Professor Belfrost's science class is back.
Hi, welcome back to my class. Today we'll have our last lesson, the chapter of two-dimensional kinematics, and we'll do a little review. Okay, so let's review for our last lesson. So if we know that Rs and Ry, then we can find the x and y component using the magnitude of R and theta, as shown in the slide. Also, subtraction of factor is accomplished by addition of the negative factor. So if we have a minus b, it means that a factor is added with minus b factor. Okay, so projectile motion is the motion of an object thrown or projected into the air, subject to only the acceleration of the gravity, and the object is called projectile, while the path is called the trajectory. And the motion of falling object is actually a one-dimensional type of projectile motion in which there is no horizontal movement. So the key to analyze two-dimensional projectile motion is to break them into two motions, one along the horizontal, one along the vertical axis. And you can find the maximum distance range and maximum height by using the formula that's stated in the slide. And consider neglecting air resistance here. Okay, so here's our today's discussion. So when we speak of a range of a projectile on level ground, we assume that R is very small compared to the circumference of the Earth. But if the range is large, then the Earth will curve away below the projectile acceleration of the gravity and change direction along the path. And so the projectile is farther to fall than it will on level ground. And if the initial speed is great enough, then the projectile can go into orbit. This will be in discussion another chapter. Okay, so when an object is in orbit, the Earth curves away from underneath the object at the same rate as it falls, and the object thus falls continuously but never hits the surface. And this and other aspect of orbital motion will be covered in greater depth later in the lesson on the another chapter. Okay. Now let's focus on velocity addition. So first let's learn about the concept of relative velocity. So if a person rows a boat across a rapidly flowing river and tries to head directly for the other shore, which is shown in the figure on the left, you see that his motion is actually diagonal relative to the shore. And the reason is of course that the river carries the boat downstream. And similarly, if a small airplane flies overhead in a strong crosswind, you can sometimes see that the plane is actually not moving in the direction in which it's pointed, but actually it's slightly slanted, okay, as shown in the figure on the right, okay. So in each of these situations, an object has a velocity relative to its medium, and the medium has also velocity relative to an observer on the solid ground. So, and it's shown in the two previous figures. So how do we add this velocity? So velocity is a factor. So we just use the rule of factor addition that we have discussed before. So for example, if a field hockey player is moving at 5 meters per second straight toward the goal and drives the ball in the same direction with the velocity 30 meters per second, then this will add up to make 35 meters per second, and this is the velocity of the ball relative to the stationary. And in two-dimensional motion, either graphical analytic technique can be used to add the velocities. And here, the technique in the analytical techniques, the formulas that we can utilize to do such things. And these equations are valid for any vectors and are adapted specifically for velocity. So first two equations are used to find the component, and the last two are used to find the magnitude and the direction of velocity when its component is known. So let's practice by using this example. So please refer to the figure on the right of the slide, and it shows a boat trying to go straight across the river. But here the velocity of the boat, which is v boat, is 0.75 meters per second. The river is 1.20 meter per second to the right. And now we are asked to find the velocity, yeah, the total velocity of the boat, okay, relative to the shoreline, okay. So the total velocity is the vx plus vy factor. Okay, you can see the vx component is actually 1.2. It's the river velocity. The Vy is actually the boat velocity, which is 0.75, and you can take square root of this and gain and obtain the result, which is 1.42 meters second. And how about the direction? Yeah, actually you need to decide first, determine which theta you use, the inner part between the free total and the free boat, or uh, between the free total, uh, yeah, between the free total with respect to the shoreline. In this case, we'll take respect to the shoreline, so the theta is calculated as shown, and we obtain the result is 32.0 degree. Okay, so this is second example. So calculate the wind velocity for the situation shown in the figure below. So the plane is known to be moving 45 meters per second due north relative to the AMS, where the velocity relative to the ground is 38 meters per second in the direction of 20 degrees west of north. So we are about to find the wind velocity, and please notice that the phi total is the factors of the phi wind and the phi plane. Okay, so here the plane velocity of x is 0, and the plane velocity in y is the plane velocity itself. So phi total x is the wind velocity in the x direction, and the y uh, velocity total is the y component of the wind velocity and the plane velocity. So we can create the equation as shown in the slide, and there we get what we want, like pwx. So the the phyx, the pwx and pwy, and then we can calculate what we have. And yeah, this is what we want. So the free wind is 60 meter per second, and the theta is 35.6 degree. Okay, and the wind speed and direction are consistent with the significant effect the wind has on the total velocity of the plane, and this is what we want. Okay, now after discussing relative velocity, let's learn about its relation to classical relativity. So when adding velocity, we have been careful to specify that the velocity is relative to some reference frame, and this is called relative velocity. Okay, so yeah, relative velocity are one aspect of relativity, and actually relativity sometimes associated with Albert Einstein, but actually this will be different relativity that we'll learn later. Okay, the classical relativity that we are learning right now is what proposed by Galileo and Isaac Newton, that only it is limited to a situation circumstance where speeds are less than 3000 kilometers per second. Okay, while the Einstein version is for the one that have greater speed of light. Okay, I mean the greater than 1% of the speed of light. Okay, so let us consider an example. So yeah, here's the example. Let's see the picture. So let's consider what two different observers see when the binocular drop. Okay, so one observer is on the sea and the other on the shore. So the binocular have no horizontal velocity relative to the observer on the ship, so he sees them fall straight down the mast. But to the observer on the shore, that because the ship is moving in horizontal, so it both two with the same distance forward while the binoculars are falling. Then the observer on the shore will see the curved path shown in the figure below. So the motion is actually relative. Let's see how we can apply this concept to this example. So say that an airline passenger drop a coin and the plane is moving 260 meters per second. So what is the velocity of the coin when it strikes the floor 1.5 meter below its point of release? So we need to measure relative to the plane and also measure it relative to the earth. So for part A, the initial velocity of the coin is 0 relative to the plane, so the motion is that of falling object in one dimension. And for part B, its initial velocity is 260 meters per second relative to the earth horizontally. So for A, we can make use of this formula to find the Vy, and then we just pick because square root of 29.4 actually have two solutions, but we pick -1, -5.42 because we know that the velocity is directed downwards, and this is the solution that will make sense. Okay, for B, we know that initial vertical velocity is 0 relative to ground. Okay, and the final is Vy minus 5.42, the CS part A. But in contrast, there now is a horizontal component which is 260 meters per second. So we'll need to add it up, and we gain that phi is 260.06 meter per second, while the theta is about minus 1.19 degree. Okay, so the motion as seen by different observers, one on the plane and one on the ground, in this example are analogous to this condition for the binoculars drop from the mass of a moving ship, except that the velocity of the plane is much larger. In addition, both observers will see the coin fall 1.5 meter vertically, but the one on the ground also see it move about 144 meters. Thus, one observer sees a vertical path and the other see a nearly horizontal path. How I get this number? I want you to calculate by yourself by having the data that is shown on the previous slides. Okay. Now, yeah, we are done with this chapter. This is just a very short chapter. Now let's do some review. So the first one is to find the following path A, okay, where all blocks or all grid are actually 120 meter on site. The first one is to find the total distance traveled, and the second is to find the magnitude and direction of displacement from start to finish. So you see that for path A, it takes 3 blocks to north and 1 block to east. The distance traveled is actually just simply you add these two numbers, so it's 4 blocks, because each block has 120 meters distance, so it is in total 180 meters. But for B, its displacement can be calculated by using a Pythagorean theorem, which gives us a square root of 10 times 120, and it's about 33,079 meter, and direction is about 80.4 degree east of north as shown in this. And number two, suppose that you take first of 12 meter in direction of 20 degree west of north, then 20 meter in direction of 40 degrees south of west. Then how far are you from the starting point? Okay, so you can make use of the graphic that I've sketched and answer this question. Actually, you can just um, solve this problem by extracting the x component, the y component of each factor as shown. So the factor A have ax and ay component, and their value is what I have stated on the slide. Also factor B, we have bx and by, and then we add ax and bx together to make the rx, and ay by together to make ry, and the rx is 19.4 meters and ry is minus 1.6 meters, and then the magnitude of the result factor is about 90.5 meters, where the direction is about minus 4.71 degree with respect to the x minus axis. Number three, to say that you fly 32 kilometers in straight line in the still line in the direction of 35 degrees south of west, and you have two cases to solve. Okay, so the distance you'll have to fly straight south and straight west is actually the factor component. So for the south, it means you take the sine, and for west, it's the horizontal component mean you need to take the cos. Okay, so sine and cos, and please pay attention to the angle because you are taking west. Okay, it means that you are in you are in southwest. Okay, it means that you are in quadrant 3, so you need to add 180 degree to your angle to make a correct calculation. And for number B, the distance is actually very easy to obtain. So yeah, it is as shown inside the calculation. So we have to obtain minus 26.2 kilometer for x component and minus 18.4 kilometer for y component. So yeah, say that we have A with magnitude A and 45 degrees southwest, and B is magnitude is B and the direction is 45 degrees west of north. And then we create the complex, not complex number actually. This is the factor component, the standard form of the factor statement, and its resultant. They can create two equations and get the A and B, and that's what we want. Next problem. So a ball is thrown horizontally from the top of 60 meter building and land 100 meters from the base of the building. Okay, so 60 meter is the height and 100 meters is the horizontal displacement actually. So ignore air resistance. So you have 4 points that you need to solve. So how long the ball is in the air. So yeah, you just make use of the formula that you have learned so far, and you get t equals square root of minus 2y by g, and it's about 3.5 seconds. For B part, it's very easy because you have known the formula too, that you can rearrange it to get phi 0 equals x by t, and it's about 28.6 meters per second. For the vertical component of velocity, before it hits the ground, because at first its initial velocity of the y component is actually 0, then it's just simply minus gt, and it will give us about minus 34.3 meters per second. And its velocity will both is actually just the, for the magnitude is just taking the Pythagorean theorem into account. For theta is taking the arctangent into account. As shown in the slide, this is the calculation. Okay. Next problem. So an owl is carrying a mouse to the chicks in its nest. So its position at the time is 4 meters west and 12 meters above the center of the 30 centimeters diameter nest. So the owl is flying east at 3.50 meters second at an angle of 3.0 degree below the horizontal when it accidentally drops the mouse. So is the owl lucky enough to have the mouse hit the nest? Okay. So yeah, let's take into account. So it takes about 1.56 seconds before it reaches the ground, isn't it? No, actually, because you have to take account that this 12 meter per second. Oh, I mean, because the velocity, okay, which is, what is the velocity? 3.5 meter per second is actually not um a parallel, I mean parallel to a certain axis, because it actually makes an angle which is 30 degree below the horizontal, so you need to take this into account. So yeah, we'll do as shown in the slide. So y equals v0 yt minus half times gt squared, and after that you can do such shown, and we get t equals 1.40 seconds, and this will make a slight difference from the previous result, right? So the horizontal component after calculate is about 4.23 meters. So because actually it needs 4 meters, okay, to reach its nest, so it actually missed the nest about 0.23 meter away. Next problem, yeah, you can read it, the passage. Okay, so it said it's so put with a throw of 24.77 meters. Also the speed is released at a height of 2.10 meter and throw it at an angle of about 38.0 degree above the horizon. Actually there are many explanations that you need to read by yourself, but the point is that you are asked what is the initial speed that is needed. Okay, so first we need to notice that we can create a Vx and Vy, and then by using this data we can find its total time of flight, okay, and also we can find the total time of flight too by using the horizontal distance formula, horizontal maximum distance range formula, and you can substitute this into the previous equation, the second equation, And you can solve this. I mean, yeah, you need some extra effort because I did not show you here how to do this. And you can obtain the fees actually approximately 15.0 meter per second. Next problem. This is the second last problem. So Brian Allen Del blah 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 blah. It's not very important. So he flew from 160 minutes and average velocity at 3.5 meters per second in a direction of 45 degrees south of east. So what was his total displacement? The second question is Allen encountered a headwind averaging 2 meters per second almost precisely in the opposite direction of his motion relative to the Earth. So what is average velocity relative to this air? And the third question, what was his total displacement relative to the air mass? Very easy actually. For the displacement, it is just average velocity times delta. This is just the previous chapter discussion, right? So we can get it. The magnitude is 35.8 kilometers, and of course, the direction doesn't change. It's still 45 degrees south of east. For question B, so we know the relative velocity to Earth is 3.53, and also its heavy velocity is is minus 2.0 meters per second because it's opposite. So Allen's velocity relative to air is the difference between these two velocity and brings us with 5.53 meters per second. Still, the direction is the same, 45 degrees southeast. And total displacement is calculated by using this data. So 5.53 times 169 in minute. So we need to convert into second by multiplying 60. So it's about 56.1 kilometers, 45 degrees south of east. Now number 8, the last one. So another airplane is flying in a jet stream that's blowing at 45 meters per second in a direction of 20 degrees southeast, and its direction of motion relative to the Earth is 45 degrees southwest, while its direction of travel relative to the area is 5 degrees southwest. So what is the airplane speed relative to the air mass? It is actually quite difficult question. I want you to pay attention to this question. And B, what is the airplane speed relative to the Earth? Yeah, so we know that we can create some uh, we can create some variable that needed the information that we needed. We can extract it. So wind relative to Earth, I write it as we, and yeah, you can see I extract the x and y component of the velocity. And plane relative to Earth, I make it short by writing the notation with PE. So I extract its information. I extract its factor into x and y. You see. Also for the plate relative to wind, then it's PW. Also uh I make it into its x and y component. So after we have analyzed the information, then you can create these two equation, and actually this is just the summation of the two factors that will create another factor, right? So the resultant factor that is created by another two factors. And by solving this equation, that you get that V1 is 29.6 meters per second and V2 is 33.5 meters per second. V1 is actually the airplane speed relative to the Earth, and V2 is actually the airplane speed relative to the air mass, and that's the answer. So A is 63.5 meters per second, and B is 29.6 meters per second. And done. Now here is some exercise for you. I want to take a screenshot and solve it by yourself. I have already provided the solution. So this is number 1. Take a screenshot. Number 2. Take a screenshot. Number 3. Take a screenshot. Number 4. Take a screenshot. Number 5. Done. 5 exercise that you need to work on. So yeah, here is a little quote for you before we end the lesson today. So Michael Altshuler once said that the bad news is time flies, then the good news is you are the pilot now. So thanks for watching. Subscribe, give a like, comment, and share this video to your friend. I'll be back on our Tuesday and Thursday. So keep watching and be thoughtful. And don't forget to visit my website, uh, sciencebitxyz.unaux.com. I see you on the next episode and see you.